Hello everyone, thank you for joining us. In today's webinar, we will discuss about simulation of human head exposure to mobile phone antenna radiation using HFWorks. Our solution specialist will cover how HFWorks can be used to analyze the effects of electromagnetic mobile antenna radiation on human head. In addition, the webinar will include a parametric analysis to investigate the effect of antenna position on the absorbed radiated power by human tissues. Before discussing today's agenda, let me introduce us. My name is Armin, and I'm the sales engineer at HFWorks. My colleague, Asma, is a senior application engineer within the domain of high-frequency electromagnetics. She will be delivering the technical part of today's webinar. I would like to highlight a few points. During this course of presentation, if you have any questions, please feel free to use the chat window to type your questions. We will answer them at the end of the presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Our agenda for today is following. I will briefly talk about our company, HFWorks, where we are located, and what products we offer. Then my colleague will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by HFWorks for its software users. HFWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. We have 2 office locations. Our headquarters is in Montreal, Canada, and another office in Germany. We offer 4 products in various add-ons covering a wide frequency range. Our first product is called EMS, which is used for electric and magnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, busbars, permanent magnets, actuators, circuit breakers, transformers, and electric motors. Our second product is HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency, and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is HFWorks 2D, which offers a static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is Motor Wizard, which is a template-based motor design software. It offers analytical and finite element analysis of BLDC motors. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, Asma will discuss how HFWorks can be used to analyze human interaction with radiated electromagnetic fields. Let us briefly touch upon the licensing structure offered by HFWorks. We offer three different programs: commercial, academic, and a startup program. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the programs, our licensing structure is usually annual based. The topic for today's presentation is simulation of human head exposure to mobile phone antenna radiation using HFWorks. My colleague Asma will discuss about the main challenges and side effects related to human exposure assessment to mobile phone antennas and electromagnetic radiations. I would now request my colleague Asma to take over and present the next part of this webinar. Thank you.
Hello everyone. Hello dear attendees. First of all, I want to thank you all for joining us today. I am Asma, Senior Application Engineer at HFWorks, and today I'm going to represent you today's webinar about simulation of human head exposure to mobile phone antenna radiations using HFWorks inside SolidWorks. So from the title, we can clearly understand the topic of this webinar. We will try to provide you the main challenges and side effects related to human exposure assessment to mobile phone antenna electromagnetic radiation. The studied antenna is used essentially for applications covering the GSM, LTE, and WLAN frequency bands. In particular, the capabilities of HFWorks antenna simulator will be demonstrated by showing examples of SIR and thermal effects of the studied antenna radiations on a biological human tissue. First of all, let's have a look on our agenda for today. So we will start with a small introduction about mobile and smartphone antenna applications and their side effects on human health during functioning. Then we will move to an overview about HFWorks inside SolidWorks with a quick live demonstration of the software's interface, features, etc. Next, we will go through a detailed analysis using HFWorks simulation solution to investigate the studied mobile antenna design and performance in free space and also near a human head phantom design to simulate the antenna-human interaction. And finally, conclusion. The portable terminal devices like cell phones are being popular day by day, and hence the number of mobile and smartphone users is increasing dramatically. The antennas of the cellular devices receive and radiate electromagnetic energy for large frequency bands depending on the application type. This emitted electromagnetic energy may cause serious health hazards because it can penetrate in human tissues and the part of it is absorbed in the body and the biological organism converts then this power into heat, which causes temperature rise and severe health damages due to the heating effects. So a common requirement for mobile phones is that the energy dissipated in the human tissues of the user has to be below certain standard limits. These limits are referred to as to the specific absorption rate of the phone, which is the measurement of the rate at which energy is absorbed by the human body when exposed to radio frequency electromagnetic field, and it is measured in watt per kilogram tissue. Now, before moving to the simulation part, let's start by introducing our software. HFWorks is a 3D field simulator fully integrated inside SolidWorks for RF, microwave, and wireless applications. It is an add-in inside it, so it is allowing the user to work on both the CAD modeling and also the high-frequency simulation within the same interface. So to start with the CAD modeling, SolidWorks provides a powerful parametric CAD platform treating all geometry types and allowing a quick building and editing of your geometry, or simply importing your own geometry inside it, with the ability to build multi-geometrical configurations. Next, when your model is ready, you can switch to Simulation tab and start by the pre-processing steps like the frequency setting, the material assignment, setting your boundary conditions, parameterization setting, and also meshing with many meshing options using manual and adaptive meshing. Then, the run step with many available options like the run of multi-selected studies, save after running it, and so on. After the run is done, you get your results in terms of circuit results or 3D and 2D field plots, and also antenna parameters in case of antenna solvers. We will check in more details later what kind of results we can get with HFWorks. And finally, if you want to have a multi-physics coupling, it can be done using a post-processing thermal coupling, allowing thermal analysis of your device for steady state and transient thermal cases. HFWorks covers also a wide range of applications such as antennas with all types like the printed antennas, waveguides, wire antenna, horn antennas, etc. We have also the S-parameter solver for filters, oscillators, tuning elements, directional coupling, circulator, etc. The time domain reflectometry solver, and finally the resonance solver for dielectric resonator, etc. As we already mentioned, HFWorks comes with an integrated electrothermal analysis, providing a powerful and complete thermal analysis for electronic devices, ensuring their electrothermal reliability, which is available for antennas as parameters and also TDR analysis. Now let's introduce our studied antenna for mobile phone application. It is a wideband planar monopole antenna operating from 500 MHz to 3 GHz and covering, as already mentioned, the GSM, LTE, WLAN and WWAN mobile application bands. It is fed with 50 ohm coaxial cable, as you can see here in our design, and the active part of it occupies a small size of the whole design. It is printed on the top and grounded portion of the circuit board with a T-shaped coupling feed and an inductive shorting strip, and the rest of it will be used as a ground plane. The CAD part is done using SolidWorks. So using this antenna design, and during this webinar we will go through three parts. The part 1, we will study the antenna performance in free space. Then, the second part, we will investigate the antenna performance when it is placed near a human head. This part will include also the effects of the antenna radiation on the studied human head phantom. So, we will inspect the SIR distribution and also the generated temperature rise at the head level. And the final part, We will go through parametric analysis to check the effect of antenna position on the absorbed radiated power by the human tissue. But before moving to the simulation results and revealing what we get after simulating our example, let's have a quick demonstration of HFWorks interface inside SolidWorks and which steps we have to follow to get those results. So here we are. This is SolidWorks interface. This is our antenna design. As you can see from this SolidWorks interface, here we have the SolidWorks tree with all design parts. We have here, as you can see, the HFWorks Manager tab. So this tab will be added automatically once you add the HFWorks from this add-in window. So we have to just check here HFWorks, and it will be added automatically here with all the features of HFWorks simulator. From this tree you can see two different configurations. What are these configurations? Since we will study the antenna design in free space and also with near a human head, so we need two different configurations, which is possible inside SolidWorks using the SolidWorks multi configurations. As you can see here, we can just right click and select show configuration, and it will allow you to switch from one configuration to another. So here we have the antenna with the human head phantom with all the corresponding studies activated here, and we can come back to the first configuration for antenna in free space by just showing configuration, and it will be shown here. This is our antenna. Let's come back to our HFWorks tree. So here we have already solved study, antenna study. Let's check the different steps that we should follow to create a new simulation antenna study in HFWorks. So to create a new study, you have just to right click here or from the assembly title, and we have here the different study types. As we already mentioned, we have the antenna as parameter, TDR and resonance. In our case, we have to create a new antenna. So from here, just to add it to this configuration, antennas. So a new PM page will be opened. We have here all the settings needed to create a new study. We start with the first tab for general properties. We have here the name of your study. You can modify it. We have the different solver that you can use it, the direct solver, the iterative solver, etc. We have here the first and the second order. If you want to have more accurate results, you can use the second order for high accuracy. We have also the checkbox for parameterization if you want to add your parameterization. We have here the port solution only if you want to solve only the port solution, or here if you want to solve also the 3D field data, and in case of breakdown level you can check this checkbox. Let's move now to the second tab, which is for frequency sweep. As you can see here, the default is using only single frequency, or you can switch to another type. We have the discrete sweep solution and also the fast sweep. You have to mention your first frequency, the end frequency, and also the number of frequency that you wanna use. All of frequency will be added automatically here to this data grid. Next tab is for meshing. As you can see, we have many options. We have the adaptive, the manual, and also adaptive from existing if you already created the mesh and you want to continue meshing using adaptive from this initial mesh. So for each meshing options, we have the needed data, like here the delta S, maximum number of passes, etc. Same thing for manual. We have many other options. And finally, the final tab is for the coupling case. Here we have the thermal coupling. So once it is checked, a post-processing folder for coupling cases, thermal coupling cases, will be added automatically. You can check it from the beginning like what we did now, or you can simply solve your electromagnetic analysis and then check the thermal coupling as it is a post-processing solution. So once you did all of that, you have to just validate your study, and the new study will be created, as you can see here. We have many sections here. The first section is for materials. Your parts are added here automatically, and you have to just right click and apply material to assign your materials. We have here a favorite library that you can use, or even the materials that you already used for recent studies, or just clicking and applying materials. A well organized and rich material library will be opened, as you can see. We have many categories, general including the vacuum, the PEC, etc. We have cables, we have substrates, we have also metals. We have also a new category including the biological materials, like here we have the liver, the muscle, the blood, etc. Also for food and agricultural materials, and finally for some composite and mixtures materials like the coal, the granite, asphalt, etc. Once you selected your material, you have to just right clicking here, like here for air, and validating, and the material will be added automatically. To edit it, just right click and edit material, and you can just clicking inside the field and change your property. Once we finished with material assignment, you go to the next step, which is settling your boundary conditions. We have many boundary conditions according to your study needs. You have to apply here like the port, lamped port. We have also for perfect electroconductor and also imperfect for the lossy conductor. We have the radiation boundary conditions, etc. Once you finish it with your boundary conditions, you go to the next step, which is the meshing step. If you have adaptation, just creating mesh. If you have manual meshing, you can apply mesh controls from here. So you will select on which you will apply a mesh control, edges, faces, etc. And that's it. This is what you need to do before solving your study. And once it is finished, you just right click and run. For the thermal solving, it is enabled only when you finish solving your main electromagnetic part, and then you can settle your thermal coupling setting with your needed inputs. Now, since we already solved our study, we have here, after solving your study, a new section of results will be added automatically with all results types. We have the first section for electric field 3D plotting for electric field, magnetic field, loss densities, and here this is a calculator to compute your conductor and dielectric losses quantities. Let's try to plot. For example, if you have here, you want to plot the electric field. As you can see here, this is our electric field. This is the scale. We have here many options to play with. If you want to change the type of the coordinate system, or the unit, or the type of plotting, continuous or discrete. If you want to change here the frequency also, you can do it, and the study is automatically updated. If you want to just to show the electric field in a very specified component or phase, this is for a selected phase and this is for selecting body, you have to click here to show your field. And you can also inactivate and activate your mode if you have more than one mode. And here the inputs, the excitation power. If you have, for this case, the default plot is for 1 watt. You can increase it, putting for example 10 watt, and the results will be updated automatically. And also the phase. This is for the electric field. Same thing could be done for the magnetic field, the losses, like you have here. We have two types of losses. We have the volume loss density in case of dielectric losses, and also the surface loss densities in case of conductor losses. We have also the port solution for the electric field inside the port. we have here for the coaxial import. We have also the magnetic field. We can play also with setting of these vectors from this vector options. If you wanna increase or decrease the density from here, and also if you wanna play with the length of your vectors, everything shown here, the type of 2D and 3D shape, etc. And we move to the second folder, which is for your circuit parameters, the most important results. If you wanna plot your return losses or insertion losses, you just right click to the plot and you select S11 results, for example with dB unit, and just validate. And you will get this is the S11 results, and the right side here is including our curve setting and plot properties, curve axis, legends, etc. You have, if you want to change the color, play also with the axis, everything is here. Same thing if you want to plot a chart plot, Smith chart plot, clicking here, adding, for example, we have the all other types of results here, the S11 results, and you will have this plot. You can, as we said, play with it if you want to add some markers like here circles, change the color, etc. And finally we have the results of antenna parameters, from which you can check your gain, you can plot your radiation pattern, etc. We already here solved our results. Let's check it. We will have here the different frequencies, the excitation power, we have also the gain, maximum delivered gain, directivity, total efficiency, everything is here. And for the plots, you can plot, for example, your 3D polar plot. If you want to show, for example, the gain for the 900 megahertz, you have just to select the frequency. If you want to show with the model and using the dB unit, this is for the 900 megahertz. We have also for 245 gigahertz, etc. So let's come back now to our presentation to investigate our obtained results. So the next figures are showing the simulated return loss and Smith chart plot of the studied antenna in free space. As can be shown, the antenna is generating two wide operating bands. The lower band around 900 MHz, which covers the GSM applications, and the higher band around the 245 GHz and also the 2.8 GHz, which covers the LTE and WLAN applications. Same thing for the far-field antenna parameters. We got the next 3D gain patterns for and the corresponding 2D polar plots for the studied antenna. We selected the first resonant frequency for the lower band at 900 MHz and the 245 GHz for the higher band. As seen, the antenna behaves with the good omnidirectional radiation pattern, which confirms the stable radiation characteristic of the studied antenna over the lower band compared to the higher frequency, where we see more variation on the pattern. The two-dimensional radiation patterns for phi angle equal to 90 degrees are superposed and shown by the right plot for both studied frequencies. Let's move now to the second part, which is studying the main purpose of this webinar, which is the effect of electromagnetic radiation of the antenna on a human head tissue. For this reason, a human head phantom is added and placed near the antenna with a distance of 5 mm. Since the modeling of the biological body is somewhat difficult because it is a lossy dielectric material, The dielectric properties such as the permittivity and the conductivity of the human body play a significant role in the interaction between the electromagnetic waves and also the biological tissue. So, a single material is assigned to the head part with an equivalent material properties that are modeled closely to the real human head. We have here a permittivity of 42.61 and conductivity of 1.48. So same work will be done for the second simulation. We have to just switch to the second configuration with the human head and solve your study to obtain the following results. This simulation can give us an important insight into how the homogeneous head model, or also call it the SAM phantom, could affect the performance of the mobile antenna. Here, it can be seen that the return loss data presents a tight curve shifting to the resonant frequency compared to the free space performance defined by the red curve. Same thing for the radiation pattern and radiation efficiency. They are also affected with the presence of a human head. The right figure is showing the maximum obtained gain with the value of 4 dB for the high frequency of 245 GHz. So we move now to the second important results, which are the specific absorption rate distributions, which define the rate of the absorbed energy by a human body and which should be within restricted limits, as we already mentioned it before. HFWorks allows to plot the local SAR distribution over the whole body mass density. So, for the input powers, we will use 24 dBm for the lower frequency of 900 MHz, which is equivalent to 250 mW. And for the high band frequency of 245 GHz, we'll use 21 dBm, equivalent to 125 mW. We got the next SAR distribution results over the human head phantom, shown by the following figures. As noticed, both characteristics are not exceeding the restricted limits defined by the FCCC, which is the Federal Communication Commission. So, the SAR value is highest around the human ear, where it faces the maximum of incident waves. The next results, which define the thermal behavior, the temperature rise coming from the conversion of the absorbed power by the human head into heat. To check the thermal effect of the electromagnetic radiation on the human head tissue, for a cold duration of 10 minutes, equivalent to 600 seconds, the transient thermal solver of HFWorks is used. So for the same input powers already mentioned in the precedent slide, which means 24 dBm for the first frequency and 21 dBm for the higher frequency, we got the following results. As seen, a local temperature increase is obtained across the human head tissue near the cell phone antenna position. The thermal behavior follows the electric field and also the SAR behaviors, which are dependent on the frequency of the incident waves. It increases by 0.25 degree for the 900 MHz and by 0.14 degree for the 2.45 GHz, which are within the reasonable limits and could increase more with time. We move now to the final part, which is using a parametric analysis with varying the distance between the studied antenna and the human head, in which SolidWorks allows the variation of the geometrical distance with HFWorks simulation results in a single parametric study and in a single project. Let's check the HFWorks interface and the setting of the design scenarios. So we have our parametric analysis with thermal also on. We will check the thermal results for each scenario. So the geometrical variable that we will play with is the distance between the antenna and the human ear. It has a default value of 5 mm. Now, this parameter variable will be added to parameters to use it as the geometrical variable inside parameterization. For our design scenarios, as we can see here from this interface, we can play with the geometrical variables, also simulation variables, which means we can vary the mesh controls, also the boundary conditions, etc. In our case, we have only the geometrical variable, which is the distance between the head and the antenna. It will vary between a minimum value of 2.5 mm and a maximum value of 20 mm with a step of 5 mm. We will obtain 5 scenarios. So after solving the study, we get the next results. We'll have the electromagnetic results and also the thermal result for each scenario. Let's check, for example, the electric field. If we'll plot the electric field, this is for the first scenario. Let's check it inside the human head. Here the electric field for the human head. This is for the different scenarios. From the scenario 1 to scenario 5. Here for the electric field, also we can plot it for the local SAR distribution. Same thing for the thermal results. If you want to check our temperature results inside the human head, we have to plot for the final time step of 10 minutes. Here we have the delta T, the temperature rise for the first scenario and for the rest of scenarios. Let's analyze now our obtained results. For the frequency of 2.45 GHz, the left figure is showing the 2D plot of the variation of the maximum attained local SAR versus the gap. As noticed, the increasing of the distance between the two concerned parts reduces the rate of the absorbed energy by the biological tissue. The right figure is animating the electric field density versus scenarios. From the smaller distance to the bigger one, the E field is following the SAR behavior and decreases from 52 volt per meter to 23 volt per meter around the Earth zone. And here, the ISO figure of the local SAR distribution for the first and the final scenarios. A difference bigger than 2 watt per kilogram is noticed between the two distances, which confirms the importance of the mobile phone position vis-à-vis the user head. And we conclude with the thermal behavior versus scenarios. The delta T, which is the temperature rise, decreases from 0.15 degrees Celsius for the first distance of 2.5 mm to the 0.034 degrees Celsius for the final distance of 20 mm. It is concluded that the antenna position causes a significant impact on the SAR and temperature rise within the human head. So, for a safe call, it is very important to take into consideration this factor, especially for a frequent use of the mobile phones. More investigations could be done concerning the main factors affecting the human and mobile phone antenna interaction, including the antenna rotation, the antenna surrounding isolation, and even the optimization of the antenna design to reduce its SAR and thermal effects. We conclude with these results. During this webinar, we saw how HFWorks presents a powerful tool to analyze and investigate the human interaction with the radiated electromagnetic fields from today's surrounding RF technologies. Also, a parametric analysis coupled with thermal survey allowed to investigate the effect of the gap distance between the antenna and the human head on the SAR and thermal distributions within the human head. The human head also affects the antenna performance and should be more investigated in upcoming works. Thank you all for joining us today. If you have any questions, please use the chat window to type them. Thank you.
Now, let us do a quick recap on HFWorks products and their related applications. We can divide HFWorks offerings into two categories: applications related to low-frequency simulation and applications related to high-frequency simulation. Within low-frequency category, we offer three products: EMS 3D, HFWorks 2D, and Motor Wizard. These products can be used to design and simulate applications like cables, insulators, busbars, solenoids, magnet arrays, eddy current breaking, wireless charging, transformers, electrical machines, etc. Within high-frequency category, we offer one product, HFWorks. This product can be used to design and simulate high-frequency applications like antennas, waveguides, filters, resonators, connectors, etc. To get more information on the software packaging and pricing, you can connect with me after this webinar. HFWorks offers various free learning resources. With the software purchase or trial, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all users of HFWorks software. I encourage everyone to try our software and experience its capabilities. Upon trial request and user qualification, we offer 2 weeks of free access to the limited version of software. In this limited version, users can access many predefined model examples and tutorials to learn more about the software features and capabilities. To request for a trial license, visit our webpage www.hfworks.com. Go to our Contact Us page, fill in your information, and submit your request. One of our representatives will reach out to you. I would like to thank you all on behalf of HFWorks for participating in this webinar. Please feel free to contact us after this webinar to get more information on this product. Thank you.